Okay, in this podcast we're going to talk about the same trend, which is ionization energy, and you'll see that there's a lot of similarities in what we're going to talk about here with atomic radius, because if you remember, all of these trends are due to Coulomb's law, and they affect these different properties in a similar way. Okay, so ionization energy is just what it looks like in this picture. It's the amount of energy required to remove an electron from an atom. The term is a little bit misleading because it's called ionization energy, but it really probably should be called cation energy, because it's only about the energy required to make a cation, to make a positive ion, to remove an electron. Okay? Okay, so ionization energy is the energy required to remove an electron, and that's going to be a valence electron, right? It's always going to be removing an outermost electron. And usually the units of this are going to be kilojoules or kilojoules per mole. Okay. So why does this take energy? Well, the electron, pulling it off, must overcome the attraction from the nucleus. Okay? So let's look at what's the association between ionization energy and chemical reactivity. Is it going to be an element that has a high ionization or a low ionization energy that's going to be more reactive? So think about that and go ahead and answer. Okay, so as it turns out, it's going to be the lower the ionization energy, the more reactive. Because reactive means it becomes an ion easily. It doesn't take much for it to lose an electron, and once it loses an electron, it's going to bond with something, form an ionic bond with something. So the lower the ionization energy, the easier to form an ion, right? Form an ion, and that makes it reactive. If it's positively charged, it's going to be looking to react with something else. Okay. So if we look at this graph here, it shows the trend. So here's the atomic number on the x-axis, and it's the ionization energy on the y-axis. So I can look and see that as I go from the start of one group as I go from lithium to beryllium to boron to carbon to nitrogen to neon, I am increasing the ionization energy. And that shouldn't surprise you, because as I do this, I'm increasing my effective nuclear charge. I have the same number of shells. I'm adding protons to the nucleus and electrons in the outermost shell, causing that Q1, Q2 to be larger in Coulomb's law, causing there to be more and more attraction, making it more and more difficult to remove. The trend is not quite as clear as I go across a period. I'm going from lithium to sodium to potassium, or from fluorine to chlorine. So across down a group, the ionization energy tends to go down a little bit because that electron is further from the nucleus, right? So the further away from the nuclear pull, the easier it is going to be to remove. Okay, so go ahead and try to answer this question. Which of these is going to have the highest ionization energy? Okay, welcome back. So as it turns out, the atom that has the highest ionization energy, these guys generally don't make ions, so we don't even publish. They're not even published. So what does that leave? Which atom is going to be the highest in ionization energy? Let's not even look at this list yet, but so it's going to be one that has a higher nuclear charge as I go across, and it's going to be further up on the table. So it turns out fluorine is the element that has the highest. So if I look at this list here, what I have is I have carbon, nitrogen, oxygen, aluminum, and silicon. So the smaller I am, and the further to the right where I am adding electrons, so my answer is going to be oxygen. Okay, so it's possible that an atom will lose more than one electron, or that an ion will lose another electron. So many electron atoms can lose more than one electron. So the first ionization energy, as you know, is the energy required to take an element and to lose an electron. So I can say I have some element X, and it becomes positively charged and removes an electron. Now this guy, the positive ion, can have a second ionization energy where now it becomes a 2+ and loses another electron. Okay, so we can think about that happening in 2 steps. So you can be a first ionization energy or a second ionization energy, or it turns out a third or a fourth or a fifth ionization energy. Okay, so here's a chart. I want you to take a couple minutes and try to make sense of it. Here I am listing the elements by increasing atomic number. That's what Z is, atomic number. And you can see the number of valence electrons here. So let's see what happens in this table. If you notice, there's this stair step between the white and the blue area. And what marks that white and blue area? Think about it for a minute. Okay, what marks that white and blue area is, in the white, I am removing valence electrons. When I get to the blue area, I am removing core electrons, right? Inner electrons. So if I just look at a lithium, for instance, the first electron is easy to remove. When it makes a big jump in energy, that jump is occurring because now I am removing electrons from essentially a helium electron configuration. So it's a full outer shell. If I'm beryllium, I can lose the first 2 electrons pretty easily, but that third electron is now I am removing it from a noble gas configuration. If I look at fluorine, you know, I can remove the first 7 electrons without too much difficulty, but if I look, there's this big jump when I get to the 8th electrons, because now I am also removing from a noble gas, or from, in all cases, this is going to be essentially removing from neon. Okay, so let's take a look at what would happen with a boron atom as an example. So if let's say I have boron, and it's a 1s2, 2s2, 2p1, right? My first ionization energy is going to remove this electron. And it turns out that IE1, which is ionization energy 1, is 0.80 megajoules per mole of boron atoms. And now I have a boron +1 ion. So I have a 1s2, 2s2. So my second ionization energy is going to remove one of these guys. And when that happens, the ionization energy, the second ionization energy, turns out is always going to be larger than the first. They're somewhat cumulative, 2.43 megajoules per mole. My third ionization energy, let's think about where boron is. It's got 3 valence electrons, right? So now I have a boron 2+, and I am going to remove that second 2s electron, and this is what I'm going to end up with. So this is ionization energy 3, and this is a 3.66 megajoules per mole. When it loses its third electron, now that is the last. It's already lost its valence shell, right? It's lost 3 electrons. It is now down to basically a helium electron configuration. So that's a very stable configuration, and trying to remove an electron from that is going to be very difficult. So the ionization energy for is 25.02 megajoules. So you see we went from 0.8 to 2 to 3 to 20, big jump to 25, much more energy when I'm trying to remove them from a noble gas shell, or from a core, right, from the noble gas configuration in the core. Okay, so there's a little typo on this part in your packet, so if you could fix it. Consider the table of the first 4 ionization energies for an element, and the question is which, and this should say group, not period, is this element in. So if I go from 578 to 1817 to 2745 to 11580, where is the big jump? Answer that question first. Is it between the first and second, second, third, third and fourth? Okay, so if you said it's between the third and the fourth, then you were right, which means not so hard to remove the first 3 electrons, much more difficult to remove the fourth, which means I must have 3 valence electrons, which means 1, 2, 3. So it must be in group 13. Okay, now here, take a look. Predict the group in the periodic table in which an element with the following ionization energy is most likely to be found, just like we did. Go ahead and try that one, and we'll take a look. Okay, so if you said that the big jump was between the 4th and the 5th, it's relatively easy to remove the first 4, becomes much more difficult with the 5th. That would suggest that the ion must have, or the element must have 4 valence electrons, 1, 2, 3, 4, which is going to put it in group 14. Okay, and we're going to stop right there.